We're Group 10, and we are focusing on the analysis and redesign of a personal coffee maker for our project. The primary function of a personal coffee maker is to brew smaller amounts of coffee for the consumers by boiling the water and straining it through the coffee grounds.
The target customer for our coffee maker is going to be those who enjoy making coffee in smaller sized portions. The primary customers are going to be those who intend to use the product in a communal use, like an office or restaurant, with the secondary customers being those who would like to use this product at home for personal use.
So here's our fast diagram showing the basic functions of a coffee maker. First we have boil water. In order to do that, we add heat, we contain fluid. Next we have filter coffee. We strain the grounds and contain the grounds. To ensure dependability, we'd like to maintain pressure. To assure convenience, we want to prevent burns and collect coffee. In order to prevent burns, we guide pouring, we direct boiling water, and we direct coffee. To enhance the product, we stop heat, and we serve individuals. In order to please the senses, doesn't need anything further, it's already coffee. So here is our first assembly sequence. As you can see, the 6 sub-assemblies along the top and the bottom left come together in the end to make the coffee maker on the bottom right. For the assembly sequence, we gave ease of transferring and handling a 1, ease of locating parts a 2, ease of fastening and joining a 2, testing sub-assemblies a 2, and assembling in parallel is a 2 for a total of score of 9. Alright, so for the second assembly sequence, not much has changed. The sub-assemblies have remained the same, but the order in which the parts are arranged in these sub-assemblies might have changed a little bit as well. On the bottom right, the way that the sub-assemblies are put together has changed a little bit, but overall it remains the same, and the score remains the same at a 9.
This is our function component mapping matrix. All of the components in the vertical column there come from the bill of materials, and all of the functions along the top row are derived from our FAST diagram.
On this slide, we have the first 20 items of our original bill of materials. And this slide has the remaining parts for our original bill of materials. This slide shows our bill of materials for our post-DFA work. Changes can be seen in red and include changes to material price, estimated manufacturing price, handling and insertion codes for the button holder, button circuit board, red button, and button rubber. This slide shows the remainder of the bill of materials for our post-DFA work. The main changes being seen are a redesign of the jug handle and redesign of the metal ring. The total cost for our bill of materials has dropped from $73.05 to $69.87.
So here's our quad chart. This shows all the parts from lowest to highest importance and lowest to highest cost. The functional component mapping matrix has functions in order of importance from left to right. If it had a function on the left, or if it had more than one function, we ranked it as high importance. The bill of materials, if it had a cost of more than $2, we listed it as a high cost. We then put it in this chart, and this informed us of what we needed to redesign later in the project.
Our product family's design focuses on our secondary consumers and includes a cup stand and splash guard, both of which are made of thermoplastic and made by injection molding. The cup stand has a slide fit interface, and total cost is $1.96, while the splash guard is simply placed on top of a single serve cup, and total cost of $1.82.
The only functional difference between the two groups is the allowance of individual servings for the secondary customer group.
Taking the results from the component mapping matrix and the functional differentiation table, we have identified several modules that would allow more efficient production of the product. Since the product variations are based on serving size, we have identified the single-use stand, splash guard, and jug components as modules, while the rest are standard platform components.
Here we can see the product family design for both our primary and secondary customer group in both assembled and exploded views. Our primary customer group focuses on large servings, while the secondary is for single serve. The part interface that's consistent between both primary and secondary groups is a slide fit interface, which is shared by both the cup holder and jug.
The secondary variant allows the user to replace the coffee pot with a mug or cup, so therefore it does not require the coffee pot to be a part of the assembly. The secondary variant does, however, include the cup stand and splash guard at the end of its assembly.
The first part of our design for manual assembly is changes to the jug handle. Originally, these were two separate parts, the jug handle and jug handle lid, but we decided to combine them into one part and use DFA guidelines 1, 4, and 3. The handling time and insertion time both dropped, the assembly efficiency increased slightly, and the assembly cost also dropped. The second part of our design for manual assembly include changes to our metal ring and metal ring holder based off of DFA principles 2, 3, and 10. The handling time stayed the same, the insertion time dropped, the assembly efficiency slightly increased, and assembly cost slightly decreased.
For our design for automated assembly, we focused on the button subassembly. On the left-hand side, you can see the exploded CAD that show the button holder, the button circuit board, the button rubber, and the red button. On the right-hand side, you will see an analysis of what it took to manually assemble this subassembly, along with the cost to assemble. This slide shows how our button subassembly has been improved for automated assembly. On the left-hand side, you can see the circuit board. It has been redesigned with the LED that's now in the center. The button rubber now has button pads on the top and bottom, and the red button has clips that allow it to be installed in any direction. The right-hand side is the automated analysis for assembly that also includes cost to assemble.
From the process selection table, it was determined that the process that best matched the needs of our redesigned metal ring was sheet metal working. The ring's function was identified to be guide pouring because it's critical in combining the handle and the jug into a single unit. Thickness and ring diameter were the two critical dimensions of this part.
To select a process to actually manufacture this red button, we kept in mind that the main function of this red button is to stop the heat, and the critical dimensions for this little part include the main body diameter, the retention lip, and the switch contact height. Through our process selection, it was determined that injection molding would be the best way to manufacture this.
Manufacturing prices were obtained for both before and after designs by analytical methods and by also submitting to hubs. The analytical analysis showed a 4-cent decrease per part after the modifications were made for a batch of 150,000 units. The quotation provided by hubs for the original design came in 16 cents cheaper than the analytical methods predicted and increased by 9.5 cents after the modifications. This difference can be attributed to differences in material and possibly different assumptions in the manufacturing process.
While looking at the design for manufacturing this red button, we looked to change things that would increase its manufacturability. There's a power symbol on the top that is now a 360-degree symmetrical icon, so that would increase symmetry. At the bottom, there's a switch contact edge that is now 360 degrees symmetrical. On the side, there are now integrated fasteners every 90 degrees.
Instituting a beverage service would complement our product exceptionally well. The made-to-order beverage service would remove the initial investment required by the customer to purchase the coffee maker. The customer would then also have their drink made fresh for them after they order. On top of improving the customer's experience, the beverage service would significantly decrease the impact on the environment by utilizing reusable coffee filters and also by serving the drinks in recyclable paper cups.
All right, so some conclusions and design critiques. So the design for manual assembly, the jug assembly, we were able to reduce the price by a significant amount. We removed a lot of unnecessary features, we combined a lot of parts, and we were able to introduce snap to fit instead of small screws. For the button assembly and design for automated assembly, the price actually went up, and we found that automated assembly was not practical due to the small batch size. However, the total cost of the product remains high. Because of the small batch size increasing the tooling cost, were we to increase the batch size to 1 million, we would probably see about a 10% decrease in tooling cost. And the high operating cost of $60 an hour, were we to shift to a cheaper labor force like China, we would probably see around 25% reduction in cost. Were we to go back and redesign this, there are a number of parts that we could combine together to continue to reduce our cost, and we would have done so.